All right, now let's look at the second case. In the second case, um, we use the measurement on the idler photon or the gate photon to put the signal photon in a maximally entangled state, in a superposition state. And that state looks like this. Oops. It's an equal superposition of horizontal and vertical states. And by the way, we can see it's also what we called psi 45 degrees previously. So this superposition state corresponds to the classical state of a diagonally polarized linear beam. In any event, after the light travels through the interferometer, though, the wave function will look different. First of all, the horizontal component of the beam will travel one distance um, through, through the interferometer. And so it'll acquire a phase difference. I'm sorry, a phase shift. And the vertically polarized component will similarly travel through the interferometer. But because it's traveling along the other path, the distance that it travels might not be exactly the same. So it will arrive, in principle, out of phase. So here I've said that the phase shift for the vertically polarized beam is e to the I phi plus phi, where phi is the phase difference. And we can write this as e to the I phi over root 2 times, let's say, h plus e to the I phi v. Okay? Great. Just as before, the effect of the last polarizer at 45 degrees is to project the wave function into the new basis. And so the wave function after the polarizer would look like this. And the probability of getting a count, assuming the detector is perfect and so on, we found works out to be psi 45 degrees psi f, absolute value squared. And now we can evaluate it and see what it looks like. So bear with me, it's just will take a couple of steps. And the result is kind of nice. Okay, so then this should be, well, we're going to get a factor of 1 over root 2 from the first wave function and a similar factor from the second one. So knowing that, let's just neaten things up by bringing that factor of 1 over 2 out of the expression. Okay. Then we have the following. For psi 45, we have this. And for the new state, we have h plus e to the I phi v. Oh, and then we have this overall factor, e to the I phi. And then the whole thing is squared. I'm sorry, I ran out of room there. So that's 1 over 2 And now we can start evaluating this, this product here, this inner product. So we have H, that's 1. We have V times e to the I phi times V. That's e to the I phi. And then we have the cross terms, H acting on e to the I phi V and V acting on H. And those terms both give 0 because V and H are orthogonal vectors. Okay? Very good. And just to be clear, this isn't just, of course, this is not just squared, it's absolute value squared. Here, we can bring the e to the I phi factor outside of the absolute value squared, and we would get absolute value squared of that term, which is just 1. And then we have 1 over 2 times this term here. Now we can play a nice trick. Let's factor out a factor of e to the I phi over 2. Then what we're left with is e to the minus I phi plus over 2 plus e to the I phi over 2. And we can see then that what we have is e to the I phi over 2 times, and now this term, e to the I phi over 2 plus e to the minus I phi over 2 divided by 2, that's just cosine of phi over 2. And so the result now, once we take absolute value squared, is that the phase term will drop out, and we'll just have cosine squared phi over 2. So the detection probability will be cosine squared phi over 2, where phi is the phase difference between the wave function components that travel on each of the two paths in the interferometer. So now this, of course, is very sensitive to the exact value of phi, and so that means we're going to see interference. Right? Because what we expect is that if we look at p as a function of phi, we should see, well, we should see it vary like cosine squared. So when the phase difference is 0, we should have a probability of 1. And then when it's the phase difference is pi, we should have 0 and 2 pi. It should be maximal again, and so on. Okay? So in this case, quantum mechanics predicts that we will see interference. All right. Just to sum up now, let's go back to the top. Look at this drawing again. So what we expect in this experiment is that we either will or won't observe interference depending on the initial state of the photons, the polarization state of the signal photons. But what's interesting is that the polarization state of the signal photons is, in a sense, controlled by our measurements on the idler photons. That's saying that we can get a different result. Either we do see interference on the signal beam path, or we don't see interference on the signal beam path. And the difference will depend on the measurement we do on the idler beam path. So that's really bizarre. It's telling us that a measurement on one particle in an entangled pair, way over here, way over there, can affect the results of a measurement on the signal beam photons way over here.